Okay, Laura, so you're okay on the first 5, is it? So I'll start on question 6. And we want to differentiate it twice, okay? So the first one will be, when we differentiate y, we'll get dy dx, okay? And then when we differentiate again, we'll get d squared y dx squared, right? That's just what we call it, right? Or another way of saying it, if this was f, we could go f dash of x and then f dash dash of x, okay? So either way of writing it is fine. Okay, so y equals the square root of x. Well, if you look at your logbooks with the indices part, you know that you'll be able to change that to y equals x to the power of a half. Okay, so bearing that in mind, if I want to differentiate, then, well, we'll just take out x, we multiply down here by a half, and then we'll reduce the power by 1. So a half minus 1 is minus a half. Right, so that's what it is after differentiating the first time. Okay, so that is when I differentiated once. I have to differentiate it a second time, so I'll be multiplying the number in front of the x by the indices. So a half multiplied by minus a half is minus a quarter x, and then reduce the power by 1. So a half taken away 1 is minus 1 and a half, or another way of saying it, minus 3 over 2. So that's the first one done. Okay, second one, Laura. Very similar. I'd say after you looking at that one, you'll probably be able to do the second one yourself, but here it is anyway. But try it first. Pause this video and try it yourself. 2x plus 3. Okay, so we need to rewrite it. So y equals brackets 2x plus 3 to the power of a half. Alright, now don't do, the reason I put it in the brackets, if I do this, then that half is just referring to the 3. Okay, so when I put it in brackets, it's all to the power of a half. Okay, so if we look at this then, we need to use our chain rule. The reason we need to use our chain rule is because we have a function in a function. Okay, so like for instance, what I mean by that is, here's a whole function, but there's also another function inside that. Okay, generally when there's an indices up here and something here, it's chain rule anyway. Okay, so chain rule, we differentiate the whole thing first, so dy dx equals, differentiate the whole thing, so multiply what's in front of the bracket by a half, 2x plus 3, and then reduce the power by 1, and we get minus a half. Right, and then we take the inside piece of the function and differentiate that. 2x plus 3 differentiated is just 2. Okay, we can simplify that as well. Okay, we can say equals, well, 2 multiplied by a half is 1. 2x plus 3 to the power of minus a half. Okay, and you don't need that 1 there, but I'll just leave it. So that's it differentiated once. Differentiated again then, so d squared y over dx squared equals, so take our power, multiply the power by the number in front, so 1 multiplied by minus a half is just minus a half. Okay, and then we have 2x plus 3. Reduce that by 1 and we'll get minus 3 over 2. So that's the first bit done. But remember, this here is chain rule again. Okay, because we have this indices up here, we've like a function in a function. So we're using chain rule. We've done the first bit of chain rule, we've differentiated the whole thing. But now I must multiply it by the inside bit differentiated. And that will be 2. And simplifying that then, we will say minus a half multiplied by 2 is minus 1. 2x plus 3 minus 3 over 2. Now, personally I would leave it like that, okay, but the way they have it in the book is this. So they put their minus 1 on top, which is fair enough, and then they focus on this bit here. Okay, and if you look at your rules of indices, you can change that, okay, to this. Okay, so that's just your rules of logs there. Alright, but again, don't worry, if you got to here, that would be perfect. Right, question 8. Y equals 3x minus 2 cubed. Again, pause this if you think you can have a stab at it, then go ahead. Differentiate it once. It's chain rule, so differentiate the whole thing first. So 3x minus 2 to the power of, and 3 minus 1 is 2. And then multiply that by the internal bit differentiated, which is just 3. And this will give us 9 3x minus 2 to the power of 2. So that's differentiated once, and then differentiated the second time. 2 multiplied by 9 is 18. 3x minus 2, and then reduce the 2 by 1, which is 1. We don't have to write in 1. And then we multiply that by the internal bit differentiated, which is 3. And that will give us then 54 3x minus 2. Okay, so there's 8 done. Question 9 then. Y equals 1 over x plus 4. Right. Looking at this, I suppose, just looking at this from the beginning, you would think surely that's quotient rule, because this here is all a fraction, okay, and quotient rule is fractions. However, and you could use quotient rule if you wanted, right? But I'm going to simplify it a bit. 1 over x plus 4 is the same as x plus 4 to the power of minus 1. We can see that from our rules of indices. Remember I said rules of indices are very important here, so you need to have an awareness of them. Get out your logbook. Not sure what page it's on. Page 21. Okay, 21 your logbook will give you these rules, and sometimes you can just manipulate the function to make it a little bit easier on you. Right, so I've rewritten this function as x plus 4 to the power of minus 1. So if I differentiate then dy dx, it's chain rule again. So here we go. So minus 1 x plus 4 to the power of minus 2, multiply by, and then x plus 4 itself differentiated is just 1. Right, so that simplified is just minus 1 x plus 4 or 2, and multiply by 1 is the same as it's just itself. Differentiate again, d squared y over dx squared equals 2 multiplied by minus 1 is minus 2 x plus 4 to the power of 1, and anything to the power of 1, you can just take the 1 out, multiply by the middle bit differentiated, and x plus 4 differentiated is just 1. If you're wondering why it is 1, think about this. X on its own differentiated is just 1, and number differentiated is 0, so that's 1. So this will give us minus 2 x plus 4. Actually, sorry Laura, sorry, can we go back? Okay, I'll tell you why we'll go back. because if you look here, that's minus 2, and me, for some silly reason, forgot to put in the minus here, so we'll go back. Okay, sorry about that now. Okay, so sorry, so we'll have minus 1 x plus 4 to the power of minus 2. No, okay, sorry about that. Right, that's that differentiated once. Differentiated twice, then d squared y over dx squared equals minus 2 multiplied by minus 1 is 2 x plus 4 to the power of minus 3. So that's that differentiated, but remember we're using chain rule, so we have to differentiate the middle bit. And x plus 4 differentiated is just 1, so that will give us 2 x plus 4 to the power of minus 3. You could leave it like that, right? I personally would leave it like that. However, the book changes it, so they have the 2, and then they can change this bit here. Look, this bit here. So anything to the power of minus 3 is just x plus 4 to the power of 3 over 1. So you might be a bit confused here. If you just look, right, the 2 is fine. This x plus 4 to the power of minus 3 is the same as this, look. Okay, and you get that through your rules of logs, and they're multiplying each other, so if they are multiplying each other, we can just put the 2 on top, and I should have brackets there to show it's all to the power of 3. Okay, again, if you got to here, you'd be doing good, right? I would personally leave it at that, but the book take it to 2 over x plus 4 to the power of 3. And again, sorry, I should have put in brackets. Alright. Okay, last one then, number 10. It says, given that y equals x to the power of 4 minus x to the power of 3 plus 4x minus 1, find d squared y, which means differentiated twice. Right, so find d squared y, and then hence find the values for x for which that is 0. Now, we'll come to that in a sec. So first of all, I'm going to differentiate it, and I'm going to find out what that is. So differentiated once, dy dx, and we'll get 4x cubed minus 3x squared plus 4. Okay, and differentiate a second time. D squared y over dx squared equals 12x squared minus 6x. Okay, so we have found what the function is when it's differentiated twice, and now we want to find the values for x for which d squared y over dx squared equals 0. So find what numbers we can put in here for x that will allow that equation equal 0. So we let it equal 0, and you could do a bit of trial and error, throw in numbers here for x, see what would equal 0. Okay, but that could take us forever. So what we need to do is factorize it. Usually you'd have a quadratic equation, wouldn't you, and you'd factorize it with the guide number or your 2 brackets or the minus b formula if you want it. But we don't have a number here, so here's how you'd factorize this. You just have to do it with highest common factor. So I can take out 6x out of both. So if I take 6x out of 12x squared, I'll be left with 2x. And then minus 1 equals 0. Alright. And now what I do is I let both parts of this equal 0. So I let this equal 0 and then this equals 0. So the first bit I let 6x equals 0. So if 6x equals 0, then x equals 0. and over here I let this equal 0. So 2x minus 1 equals 0, so 2x equals 1, so x equals a half. So if I put in 0, so if I put in 0 in for x here and here, well then I get out 0, and likewise if I put in a half for x there and there, I get out 0 also. Okay, hope that helped, Laura. Any trouble, just let me know. Okay, make sure, I would think your problems, I suppose, lie in maybe not a great understanding of rules of indices. Okay, so look at your logbook, okay, and make sure you cop that, you know, the square root of x can be written as x to the power of a half. Okay, and also make sure, like this one, that you know how to use chain rule. Okay, and know when to use chain rule, I suppose, is important also. So something like this, that's product rule, okay, because there's two functions multiplying each other. Something like this, quotient rule, two functions dividing each other. Something like this, chain rule, because you have a function, but then you have a function in that function. Okay, so anyway, I hope that helps, Laura. Okay, thanks.